Okay, guys, topic of the day. It's time to address our dirty little secret. So, guys, to tee up this ball for you, what I would like you to do, and please do not do the net ionic equation, please do the complete molecular equation. Silver nitrate let's keep it simple. Table salt. Predict the products and include subscripts. You know what? I'm gonna just, so needed a little more room. Silver nitrate, table salt. Products and subscripts. And actually, Talmadge, that was the next thing I wanted to do. Maybe, you know what? Actually, this would be a great experience because they're going to do a lot of this on the AP test. Let me give you subscripts. Aqueous, aqueous. And then, guys, what I'd like you to do after you're done with this is draw a picture. And I've exposed you to this a bit. We're going to do a lot more of this in AP review in April. Draw a picture. On the AP test, they would give you a box in which to draw the picture. But guys, draw a picture of this system as it would actually take place. So let me make that sort of like what it would look like on the AP test. So aqueous, aqueous. What does it look like in a box with the understanding that that box is a beaker? Once the reactions happened. Yeah. Draw pictures. Yeah, you don't have to draw the Lewis dot structure of nitrate. It's interesting, though. What would they have you do on the AP test? I can't imagine they'd have you draw that because it's not about it being a molecule. So you can draw circles to represent species. But inside the circle, write what it is. Please draw it to scale, using arrows to represent polarities. That would be kind of funny. Yeah, it's funny because, you know, the people that grade the AP tests are actually college professors and high school teachers. And I've never gone to the AP grading, frankly, because I'd rather spend the summer with my family. But the kids whose teachers do grade the tests, the kids will typically write notes to their teachers on their tests. Yeah, so, oh yeah, yeah. Hi, Mr. Brown. Oh yeah, yeah, right. You could do that on the stats test, write little notes to Gil. The problem is you don't know which question he's grading, and he doesn't know until he gets there, so you'd have to write him a note on each question. That's right. That's right. Okay, guys, let's talk. So we obviously understand that this is a double displacement reaction where our products are silver chloride and then sodium nitrate. And I think you all figured out that your subscripts are as such, right? Okay. So then as we draw that, what are we going to draw down here in our beaker? Well, down here at the bottom, we're going to have a pile, not that. We're going to have a pile of AgCl. And then in solution, we will have sodium ions and we will have nitrate ions. It would tell you. I don't know. Understand that this is not a fully vetted AP question. This is just us talking chemistry. So, are you okay? Because guys, it turns out that this is not actually what happens. So, let's talk. So, yes, silver nitrate and sodium chloride react. Yes, sodium and nitrate are spectators. They remain in their aqueous form. Yes, sodium chloride tends to be a solid. But guys, it turns out, what did I say? Silver, sorry, silver. So yes, silver and sodium are so close in my brain, I'm getting them mixed up. So guys, yes, silver chloride tends to precipitate, but a little bit of it dissolves. Not very much, but guys, a very, very small amount of this silver chloride does in fact dissolve. Now understand, we're going to study this in a minute. Understand that so little of it does dissolve that functionally we treat it as if none of it dissolves. And that's been, it's functional for our understanding of chemistry. This doesn't change what you know about precipitation. But what we're going to do now is we are going to focus in on what this silver chloride is actually all about in water. So guys, when we do that, we've got to do this. And I would encourage you to step down and write this down with me. Silver chloride is largely insoluble. But, tipping our hat to Miracle Max, it's only mostly insoluble. Sorry, I couldn't pass that up. Guys, some of this, come on. Guys, some of this will actually dissolve. But, and I know you see this, but let's talk. What is wrong with the way that I represented that? It's equilibrium. Because guys, if it were the other arrow, that would make it completely soluble, and that would be a strong electrolyte. So understand that that is why this now becomes an appropriate conversation. Because just like we have weak acids and weak bases, we also now can talk about the gray area. Prior to today, we've said that either salts completely dissolve, strong electrolytes, or they don't dissolve at all, insoluble. Now, because of everything that you've learned in chapters 16 and 17, we can now talk about the reality that many of these salts that we previously thought were insoluble, in fact, are slightly soluble. So now, guys, let's do this. Put subscripts on these. Did you get it? So what is the subscript on AgCl? Solid. That is the stuff at the bottom of the beaker that has not dissolved. Now what about the Ag and the Cl? These are aqueous. Now guys, just as a little foreshadowing, where are we eventually going to go with this? We are going to icebox this. And when we, just a second, when we icebox this, let me do this differently. In order to icebox this, we need, well, when we icebox, we eventually end up populating an equilibrium expression, right? Products divided by reactants. So guys, let's do this. What is our Kc going to look like? Well, we've got products, Ag plus and Cl minus, and then we've got our reactant, AgCl. But you saw what happened, right? Why is this wrong? Because AgCl is a solid. It does not have a molarity, therefore it does not go in the Kc expression. But this is no longer what we call Kc. Check this out, guys. This is actually what is called KSP. So now let's talk about why KSP, because this is brilliant. The S stands for solubility. The P stands for product. Guys, what does product mean mathematically? To multiply together, but guys, check this out. Your KSP expressions will always only be multiplication processes. Why will there never be a division in a KSP expression? Because the denominator is the salt that doesn't dissolve and will never be there. Does that make sense? So guys, understand they call these KSPs because they truly are always only multiplication products, because you will never have a denominator. Now guys, how does that play out relative to the icebox? What do we have to do to our icebox? Right? Because in our icebox, remember, in the same way that we got rid of water when we were iceboxing weak bases, there is not data to include for the salt, because that's the part that's not dissolved, and therefore it has no molarity to change in the first place. Does that make sense? So guys, that's where we're going with this. We're going to solve two problems. Here's the hazard. You look at this and you go, this is easier. We're never going to have a denominator, and we're never going to have data in this part of our ice box. This seems easier. But guys, I'm going to tell you right now, these are harder than KAs, KBs, buffers, any of that. People tend to screw these up more than they screw up everything else we've done in chapter 17. So guys, all we're going to do today is solve two of these, okay? But Talmud, you had a question first. In an acid-base sense, but we're not even talking about water here. We'll never figure out the pH of this. We're just going to figure out the concentration of the pieces. Yeah, go ahead. Actually, Mark, hold on just one second. But Talmud, you're right. The pH of this solution would not be 0 or not be 7. It would be, so the silver would react with the water. It would take in some OH. It would be slightly acidic. But we're not worried about that. Go ahead. Oh, no. So, yeah, no. What you'll find is that any salt that reaches equilibrium, so it does dissolve, but just a little, these equilibria lie hugely to the left. You won't, well, never say never, but I am unaware of any slightly soluble salt that doesn't dissolve just a little. You know what I'm saying? So what you're going to find is that the values for these KSPs are on the order of like 10 to the negative 9th, negative 10th, negative 11th. So you guys good with the ideas? You ready to do some math? So guys, it goes like this. Oh, baby. Wow. I just absolutely... Here we go. Okay. So guys, we've been through all of this. Here we go. It says the K, and this is all just everything we just talked about, just using calcium fluoride rather than silver chloride. Doesn't matter. says this. The KSP for calcium fluoride, look at that KSP value, 10 to the negative 11th. What is the solubility of calcium fluoride in grams per liter? Here, yeah, just scratch it down and we'll talk. Sorry, I'm kind of in the way, aren't I? That's all the information you need. We're going to solve it as soon as you've got it written down. Okay, you guys ready to do this? So, have you written it down? Because I need a clean screen to do this. You're okay? Okay, so creating a clean screen. Oh, wait, I lost my writing tools. Just a second. Okay, we should be good there. Do this. You guys all have this. Okay, so here we go, guys. So, this is at least worth my writing down because it's always good to keep our goal in mind. So the goal here is solubility in grams per liter. Is that right? Okay, I didn't even print these, so I'm flying by wire here. So, guys, our goal here is this. Forgive me, I'm going to draw a picture. So if that's not what I wanted to do. So if we've got a beaker and there's some water in here, and we dump in some calcium fluoride. The question is, how much of this calcium chloride in grams will dissolve into a liter of water? Does that make sense? That's what we're solving for. So guys, how do we do that? Well, the first thing that we've got to do is come up with a structure that will allow us to study this equilibria. Because what's going to happen is most of the calcium fluoride is going to fall to the bottom of the beaker and it's just going to sit there in a pile. But a little bit of this calcium fluoride will dissolve. We're trying to figure out how much per liter. Okay, so in order to study this, we need the icebox. Guys, please write the products for this. Do it in your notes, right? Do it as you're doing. Do this without me. This is why these are hard. This is why you're going to screw these up. Forgive me, but you will. This is why. What does this break into? A calcium 2+ and 2 fluorides. No, that's right. Yeah. Yeah. No, that's what this breaks into. So guys, as this dissolves, for every 1 calcium, we'll get literally 2 fluorides. Now, let's set up our icebox. Now guys, this is always nice. Get rid of that. So now what we've got to do is we've got to go back and look again at what we're solving for. So guys, we're solving for grams per liter, right? And you'll notice that I'm spending the time to help you think through this because it would be easy for me to just start solving this. But guys, this is a skill that you're going to need to increasingly hone as you're getting ready for the AP test. And that's simply figuring out what you're trying to figure out. And you're trying to figure out grams per liter. And that is not contained anywhere in an icebox. But grams per liter is a whole lot like what, which is in an icebox? Moles per liter. So guys, if we can come up with moles per liter, we can convert that to grams per liter. So we need to know the molarity. But that is the molarity at equilibrium. So, traditional icebox, what do we know the initial concentrations are? 0. Now guys, be careful. This is where this will get you. As this falls apart, how much calcium will we get? X. How much fluoride will we get? Good, 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 good. 2x. So this is x, and this is 2x. But guys, this is still not the place where you're going to screw this up. Watch. I'm going to switch colors to make this stand out. KSP, that was a really ugly S, is Ca 2+. Write the next factor in the KSP expression. Did you get it? It is F, yes, minus squared. Guys, you're going to forget that. And even if you remember that, there's still the possibility, well, this is actually where you're going to make the mistake. Help me with the KSP value. I don't... 3.9 times 10 to the negative 11th is equal to... Can you guys talk to me about that? Okay, so why don't we back up and make sure you understand? So our concentration of Ca is X. Our concentration of F is 2x squared. Bringing those together results in 4x cubed. That's why you're going to mess these up. Did you all get 0.00021? Can anybody confirm or refute? I got 0.00021. 2.1 times 10 to the negative 1, 2, 3, 4. Yeah? Yep. Okay. Am I okay? I got that. 2.1 times 10 to the negative 4th, or 0.00021. Okay. Now guys, understand, we're not done. But we need to talk about what this number means. So this number tells us the molarity, and guys, I know that we're sort of, stick with me here. So guys, this number tells us the molarity of this. What if they asked us, and they didn't, but what if they asked us what would the molarity of the fluoride be? It would be twice that. But guys, here's the logic that you need to track with. What they want us to know is how much of that dissolves. So the thought then is this. This number represents this molarity, but this molarity is also representative of the number of moles of this that breaks apart. Does that make sense? For every one of these that breaks apart, one of these comes out. So now we can answer the question. And I'm going to set it up off to the right here, very condensed. There's not going to be enough space to solve it. But I'm going to set it up, it's dimensional analysis. I'll set it up here, then we'll move it and solve it in a second. So guys, our goal is grams, but it is grams of calcium fluoride divided by liters of water. That will be our goal. Our starting point will be, I'm going to draw a line here just to segregate this. our starting point is the 0.00021 moles. But guys, it's moles of what? Calcium ion. Moles of calcium ion. And what will our denominator be? 1 liter of water. So guys, with that, allow me to make this bigger now. So 0.00021 moles of calcium ion in 1 liter of water. And we want to know grams of CaF2 in a liter of water. So conveniently, our denominator is taken care of. So how do we convert? Well, guys, 1 mole of calcium ion will be created by the breaking apart of 1 mole of calcium fluoride. Now, 1 mole of calcium fluoride, oh golly, 1 mole of calcium fluoride weighs, is it 19 something? Yeah, so 19 times 2 plus about 40. Yep. So about 78.0 grams in 1 mole. So 0.00021 times 78. So guys, 0.016 grams of calcium fluoride will dissolve in a liter of water. Yeah, guys, that's 16 milligrams. But that shouldn't be surprising to you, realizing that the KSP for this stuff is on the order of 10 to the negative 11th. The smaller the KSP value, the less, well, assuming you're not dissolving something really heavy. Yes. Does that make sense? You okay? Okay, so guys, let's spice things up a little bit. No, that is not a molarity. It is a solubility in grams per liter. Now, guys, let's solve this next question and we're done. Calculate the molar solubility of calcium fluoride in a solution that is 0.01 molar in calcium nitrate. Write it down. Then we'll talk about the logic. Then we'll do the math. Calculate the molar solubility of calcium fluoride in a solution that is also 0.01 molar in calcium nitrate. Is 0.01 molar. Did y'all get it written down? You okay? Because this is going to go away. You're good? Okay. Okay. Becky, you okay? Did you want to borrow my contacts? You okay? Okay, so guys, what are we talking about? Well, let me show you. I'll switch to black so it stands out. Turn your attention back to our beaker. That beaker represents the chemistry that this stuff goes. This beaker represents calcium fluoride dissolving a little bit into water. The question that we're now pursuing is this. What if we add calcium nitrate to this? So what does that do? Well, what does the nitrate do? Nothing. So let's not even worry about the nitrate because the nitrate's a spectator. So we can get rid of that. So what we're doing is we're talking about adding calcium ion. So if we add calcium ion to this, we are now adding additional calcium ions. What does that do to the equilibrium? Which way does it go? To the left. So and guys, let's look at it two different ways. As we introduce more calcium ion, there are then more ions of calcium to run into ions of fluorine and cause that to precipitate as calcium fluoride. Or, if you prefer, as this goes up, the equilibrium shifts to the left. However you choose to think about it, what does that do to the amount of calcium fluoride that can dissolve? It goes down. Now, we figured out, in the last problem, we figured out the amount of calcium fluoride that can dissolve in grams per liter, right? Let's revisit this. That's the molarity. Guys, that is the maximum molarity that you can create for calcium fluoride. It is impossible, at whatever temperature we were at, to make this solution more concentrated than 0.00021 molar. Get the idea? Now let's solve the next question. What does the molarity of the solution become if we add calcium nitrate? So guys, we already know the molarity of pure calcium fluoride. It's 0.00021. What will the molarity become when we add calcium nitrate? Smaller. And by the way, guys, what phenomenon are we talking about as we study this? The common ion effect. Guys, this is the common ion effect. So here we go. Do it with me. Once again, calcium fluoride is dissociating into calciums and fluorides. As we icebox this, we know that these have no values. Now, guys, and I don't have the question in front of me, so you're going to have to help me. We are now talking about an environment where we have an initial concentration of which of these two products? And what was it, 0.01? So we are starting, was there a zero trailing? So we are starting with 0.010 molar calcium ion. Where did that come from? From the other substance. How much of this came from the breakdown of calcium fluoride? None. Similarly, there's none of that. Remember, the I is initial. Now, guys, what happens to the amount of calcium present as some of the calcium fluoride does break apart? It goes up by X. What happens to this? It goes up by 2X. So now we've got the concentrations we're okay. 0.010 plus X and 2X. So now we need our KSP expression. KSP is equal to calcium 2 plus, and these make me so nervous. Fluoride squared is equal, what was that number? 10 to the negative 11th. 3.9. So 3.9 times 10 to the negative 11th is equal to 0.010 plus X times 2X, the quantity squared. Now we need to talk. What are we going to do to solve this? Yep. We can get rid of this. What does that X represent? The amount of calcium that is created due to the breakdown of calcium fluoride, which we've already demonstrated to be itty-bitty. It's 0.00021 molar. Compared to the initial 0.01 molar, that's like 1,000 times smaller. It doesn't matter. So in the same way that in our acid base, we can go approximately equal to, this is actually approximately equal to 0.010 times 4x squared. That's math even I can do. 3.9 times 10 to the 11th. Divide that by 0.01. Divide that by 4. Take the square root. X is equal to, I need more significant digits, point, and I'm not even going to put it in scientific notation because it drives the point home better. Now guys, for reference, remember what the molarity was prior. 0.00021. So this actually drove the molarity down 10 times. Adding that calcium ion, the common ion, as we predicted, made the salt even less soluble, and in this case the molarity dropped from 2 times 10 to the negative 4th to 3 times 10 to the negative 5th. Get the idea? Yeah. Yeah, it's all Le Chatelier's principle. Or do you mean why some salts are only partly soluble?
I mean, when we added this into a second solution, the salt capacity to be soluble went down.
Right. Right, and that...
Only due to Le Chatelier's principle.
Right, it's all common ion effect, because what you're doing is you're adding additional calciums. As you add additional calciums, it increases the frequency of collisions with fluoride, driving the equilibrium in that direction. That's it. What do you think, y'all? Good? All right, so guys, this then is your homework. Yeah, you'll see. Here, let me stop recording.